Okay, just to tidy up and finish up the last little bit of this lesson, we left off by calculating the expected value of rolling 2 dice, that experiment, and we said that it was 7. So again, what that means is if I rolled 2 dice a lot, did a large number of trials, and recorded what I rolled on every single trial. So let's just say I rolled 2 dice a million times and recorded what I rolled each and every roll. If I took that value that I rolled on every roll and found the average, so added up all the rolls and divided by a million, the answer would be around 7. If I want to simulate that with my Inspire, here I have 2 columns for 2 die. So die 1 is a random integer from 1 to 6 1,000 times. So in other words, it's like rolling a die 1,000 times. Die 2, exactly the same thing. A random integer from 1 to 6 1,000 times. I've got a third column here which is an add the first 2 columns. So I'm going to add in a formula that adds the first 2 columns. Basically it'll be die 1 plus die 2. And then over here I've got the average, which is a formula that's going to calculate the mean of this third column, the sum of the 2 die. So here we go. I'm going to go equals die 1 plus die 2. So this is finding the sum of 2 dice. Watch the average. 6.984. Again, if I increase my trials, so I'm going to say the first die, I'm going to roll that 2,000 times this time. It gives me a syntax error because the third column is adding up 2 columns that are of different length now, but so that's where that error comes from. But this is going to go away as soon as I change the second column to the same number of rolls, 2,000. Again, watch the average. 7.016. Let's do it one more time for the maximum list length, which is 2,500. Again, I got that error because now I have 2 lists that are of different length. 2,500. Watch the average. 6.9768. I can kind of redo this. Maybe if I press enter on any column, I create a new random list, and you can see, okay, the average is always going to be around 7, and that's just for a relatively small number of rolls, which is 2,500 rolls. If I could get that even larger, you'd see that I'd get even closer and closer to 7. So let's go back to our lesson. So again, that expected value is the long-term average of rolling 2 die. Okay, if you notice the calculation of expected value, multiplying each outcome by its probability, this is actually a weighted mean. The higher the probability, the more likely that event happens, and so it has a greater say in the determination of the expected value. So notice the 7 had a probability of 7/36, and if you look at its product, it's the greatest product. Okay, so that's why the average is being pulled toward it. It's actually a weighted average calculation, just like we did way back in September. Let's continue on. Let's try this example, the lottery. There are 3 million tickets printed. The prize distribution is given in the table. Determine the expected value of the prizes, and then we're going to figure out if the game is fair. Recall, a fair game has an expected value of 0. So in other words, if I pay $1, then the expected value should be $1 to me. So that my value, I'm not gaining any money, but I'm not losing any money either. So if I lay out $1 to play, I should be getting $1 back from the expected value, and then that would be considered fair. So why don't you try, this is on your handout, this is at the bottom of your handout, try to calculate the expected value. Okay, so go through that calculation. Notice there's 3 million tickets printed, so figure out the probability of each of the prizes, and then determine the expected value in the fourth column. So I'm going to give you a chance to do that on your own. Okay, picking up the solution, I added in all my calculations. So first of all, the probability column. So there's 3 million tickets that are printed, so the probability of winning 10,000 is 4 out of 3 million. $50, 1,000 out of 3 million, and so on. For for each of the remaining prizes, 66 out of 3 million and so on. Now to calculate the expected value, I'm going to take each of the prize values. So this is my random variable. This is the outcome to the experiment. I'm either going to win $10,000, $50, $10, $2, or 1, and the probability of those happening is right here. So I need to multiply these two columns together. So 10,000 times 4 out of 3 million, which is 40,000 over 3 million. $50 times 1,000 over 3 million, so 50,000 over 3 million. So again, I've short-formed my 3 million to 3M. And all the way down to $2, which has a probability of 336,000. I think I missed a zero in there. 336,000 over 3 million, which is 720,000 over 3 million. All the way down to $1, which has a probability of 378,000 out of 3 million. So you have that's your probability of winning $1. So multiply the outcome by the probability, you get the same thing, 378,000 out of 3 million. Now we need to add this all up. So I did that on my Inspire, and this is what I got. I got 1,800,000. So 1,800,000 out of 3 million. Remember, this, you're adding up these because they've all got denominators of 3 million. And so again, when you're doing your expected value calculations, try to keep the denominators the same because you're going to end up adding them up. Now let's actually calculate what that equals. So I'm going to quickly go over to my Inspire and divide that 1 million by 3 million. Okay, and I get 0.6. Okay, so let's go over to our lesson. So the expected value is 0.6. So expected, the sum of that column is 0.6. So again, what does that mean? That means if you the average winning of every ticket is about 60 cents. If you look at it, if you look at all of the outcomes, there's 4 $10,000 prizes, there's $1,050 prizes, 66,000 $10 prizes. So these are all the outcomes. If I add up all those prize values, so 4 $10,000s, 1,050s, and divide them by 3 million, which is in essence what we did over here, your average winning for every ticket is 60 cents. Okay, so if you imagine this, if you buy every single ticket for $1, imagine you bought every single ticket for $1, you would be out $3 million. Now how much would you get back? Because you would be then guaranteeing yourself of winning every single prize. How much would you be getting back? Well, you'd only be getting back 1,800,000, or in other words, 60 cents per ticket. So is this game fair? No. The definition of fairness is that whatever I pay out, I better get back as well. So if I'm paying out $1, I better be getting back $1 in the long run as well. So this isn't a fair game because you are losing 40 cents on every single ticket. Losing 40 cents per ticket. Okay? So again, the way, just to make sense of that, every single ticket, if I bought every single ticket, I would be out $3 million. But I would be guaranteeing myself of winning every single prize. But if you look at, add up all those dollar values, it comes out to $1,800,000. So you are short. You didn't make back your $3 million. In fact, so for every $1 ticket, you're only getting back 60 cents per ticket. So you're short 40 cents every ticket. You're losing 40 cents every ticket. And if you take this 40 cents per ticket and multiply it by the 3 million tickets, it comes out to the difference between 3 million and 1,800,000. Just to finish up with a few definitions on what we've been doing. What is a random variable? Unlike just a variable, a random variable is a variable that can take on any value, but it's randomly assigned. So a numerical value assigned to a real-life occurrence or the outcome of an experiment, but the value of that variable is arrived at by chance, by some unknown probability. We usually denote it by a capital letter X. So for example, in our 2-die experiment, the random variable has 11 possible outcomes, which are 2 to 12. Okay, so a random variable, make sure you understand what that means. Now we're going to be looking at 2 types of random variables. So in this unit we're going to be looking at discrete random variables. We actually looked at the difference between these 2 words very early on in the course. A discrete random variable is a variable that only takes on a certain number of values that are separate from each other, which is what we've been doing. The 6 outcomes of a single die, 1, 2, 3, 4, 5, 6, or the 11 outcomes for the sum of 2 die, 2 through 12. So a discrete random variable takes only a certain number of values. Okay. A continuous random variable has an infinite number of possible values in a continuous interval. So an example of this would be height. Your height could take on any possible value between a minimum and some maximum value. Okay, or sometimes we can think of time as a continuous random variable. Next unit we'll take a closer look at continuous random variables and their distributions, but this unit we're going to look at discrete random variables and the types of probability distributions that we can apply to those. Finally, our notation. The probability of a random variable having a particular value x, very similar to the last unit probability, so p of x. So you do see this notation occasionally, p of x equaling some value. So for example, if I write this for the 2-die experiment, the probability that the random variable x takes on the value 7, this was equal to 6 out of 36. Okay, so you do see that. So this is saying the probability that the random variable x in my experiment, rolling 2 die, takes on the value 7. And here's the whole focus of the next 2 units in this little box. We're going to be looking at probability distributions, and you can see a probability distribution in 1 of 2 forms. Graphical form, we made those earlier, or tabular form, a table of values. And basically what a probability distribution is it's showing you the distribution of the probabilities for a given experiment. It's showing you all the probabilities that you can get for any given experiment. You see your assigned work there, and that'll be it for this lesson.